Right. Good morning, everyone. We are recording now. Are there any questions or concerns pertaining to yesterday's lecture? Right. So what we did is we took an LP, which was standard equality form, and it had some other nice properties. So you had this identity matrix, and you had a non-negative right-hand side, 17, 4, 10. And we solved this LP using the simplex method. Right. In particular, we found we found an optimal solution in this case. The last dictionary, you can see that the objective function is 21 minus x5 minus x6, which is equal to the original objective function because we have just done simple row operations, right? And that in particular means that 21 is an upper bound. And the current solution, which is 41000001, has value 21, so that has to be an optimal solution, right? I mentioned at the end of yesterday's lecture that we will discuss certificate of optimality. Actually, I'm going to postpone this. I'm still trying to figure out what is a good way to present material, a good order. So what I would like to do instead is I want to focus on dictionaries and make things a little bit more rigorous before we discuss certificates. Okay. So slight change in plans. All right. So yeah, let's start a new page, but we will keep referring to our previous LP from time to time. So maybe I'll just put down the original LP on the right hand side here. So we had maximize 5144000 x subject to 413310112123 followed by an identity matrix. Right, so things are a bit close. Sorry about that. And the right hand side was 17, 4, and 10. And we have x equals 0. Okay. Good. So let's just formalize things a bit. So what is a dictionary really? For an LP in standard equality form, let's say our LP is maximize C transpose X plus S subject to AX equals B and X at least 0 as usual. Right? Can you hear me?
Yes, sir, we can hear you.
Okay, thanks. There was something at my end, so I felt I was disconnected. Okay, so let's say we have an LP in SEF where A is an M by N matrix, right? And we are going to assume that the rows of A are linearly independent, right? So in other words, any constraint cannot be written as a linear combination of other constraints. Otherwise, you would just throw it away. So let's say you have linearly independent rows, which in particular means that the rank of the matrix is equal to M and M is less than equal to N, right? So a dictionary is a system of M plus 1 linear equations, right? So in this example, we would have 4 linear equations in each dictionary, right? Representing this LP where the objective function, which is denoted by z, and n of the original variables sorry, my bad, m of the original variables. You have a total of m constraints and n variables. So we want m of the variables. So in our example, we want 3 variables to be expressed as linear functions of only the remaining variables. Right? So the remaining variables will be n minus m. So for example, if you look at the second dictionary from yesterday, it was z equal to 20 plus x2 minus x3 minus x4 minus x6. And we wrote 3 of the variables, x1, x5, and x7, as functions of the remaining 4 variables. And it was something like this: 4 minus x3 minus x4 minus x6. Okay. Right. So here we have m equal to 3 and n minus m equal to 4. Okay, so that's what a dictionary is. And I just want to take a second look at all the solutions that we found by Simplex yesterday, right? And go a little bit deeper into the algebra behind it. So if you look at the 3 solutions that we found yesterday, so the first one is very simple. Right? It's the right-hand side of the original system, basically. And then for the different dictionaries, we found these solutions. And for each of these solutions, we can write down, we knew what the basis was, right? We talked about basis without writing formal definitions. So I'll just put down the first basis was 5, 6, 7. The second one was 1, 5, and 7. And the third one was 1, 2, and 7. And the values went from 0 to 20 to 21. So if you think about the first solution, what exactly is going on? It is simply the solution of the last 3 columns of the matrix times x5, x6, x7, and the right hand side. Right? That's very clear. Turns out for all of the solutions, this is actually true. If you look at the second solution, right, it is simply you take the first column, the 5th column, and the 7th column from your matrix. So it's 4, 1, 2, 1, 0, 0, and 0, 0, 1. And you have the entries 1, 5, and 7. And the right hand side is as it is. If you solve this system, you will get exactly right, you will get exactly x1 equal to 4, x5 equal to 1, and x7 equal to 1. Sorry, 2. Okay, you can plug it in and check. If you plug in 412, you get exactly 16 plus 1, 17, and so on, right? So these are exactly the unique solutions to these smaller systems, right? Where you just look at those columns and you solve the system and you get a unique solution, right? Which basically means that those columns are linearly independent. That's basically where we are getting at. So I just want to make things rigorous in a linear algebraic sense. Okay. So the third one, you can do it yourself. Okay. All right. So the point is, each of these 3 by 3 submatrices is a square invertible matrix. Right? That's the key point I want to make here. And now I want to use this observation to talk about some linear algebraic concepts that we will be referring to throughout the course, especially in the next 2 modules, and maybe even after. Okay, so let's say A is any m by n matrix. And again, we assume that the rows are linearly independent. And let's say I take a set of the column indices. So let's say J is a set of column indices. So what I mean by that is that J is a subset of 1 up to n. Okay, your columns are indexed 1 up to n. So I'm picking a bunch of columns. So if I want to represent the matrix formed by those columns, I will write it as AJ. This is a submatrix of A with only those columns as specified by J. Okay. For example, if I write A4, just a singleton set 4, I'm referring to the fourth column of our matrix, which is 313. Right. So in this example, A4 is simply 313. Right. And if I say A15, I'm referring to just the first and the fifth column, right? 412 and 100. Okay. All right. So that's just notation. So a set of column indices say capital B, we are also using small b for the right hand side, so I feel the need to say capital here, forms a basis if the matrix A, B is a square invertible matrix. Right? In particular, if you look at all of these sets, we call them bases, and that is the definition, right? In other words, a basis corresponds to a maximal subset of linearly independent columns. And now that you have done assignment 1, you know what maximal means, right? You can't add any more columns and keep it invertible, right? Or you can't keep it linearly independent. That's probably the better way to say. In other words, a basis is a set of, maybe I should say it's a maximal set of linearly independent columns. So in our example, we have that we have a 3 by 7 matrix. The rows are linearly independent. So it follows by linear algebra that every basis will be a set of 3 columns, right? Because the rank of the matrix is exactly equal to 3. So each basis will simply be a set of 3 columns. Some set of 3 columns, right? Not every set of 3 columns will form a basis. There are certain sets that will not form a basis. Can anyone see an example here of 3 columns that do not form a basis?
So we can have 1, 0, 1, 1, 0, 0, and 0, 0, 1. Those 3.
Sorry, which ones?
Second,
number 2.
Number 2, 1, 2, 3, 4, 5, and 7, I think.
Exactly. If you look at 2, 5, and 7, notice that the sum of columns 5 and 7 is exactly equal to the column 2. So that won't be a basis. Right? So let me write this down. For example, 2, 5, 7 is not a basis. So although it is 3 columns, it doesn't form a basis. Okay. And all of these that we found by simplex, all of these are bases, which is why we call them bases. Okay, good. Any questions or concerns at this point? So for the sake of convenience, given a basis B, we use n to denote the other columns, to denote the set of column indices which are not in B. Okay, so for example, if B is 157, then the corresponding n is the remaining columns 2, 3, 4, and 6. Okay. All right. So a solution x bar of the system ax equals b. So we are just looking at the system. We are not looking at our whole linear program in this context. Is a basic solution if there exists a basis B of the matrix A such that all of the other variables which are not in your basis, they are equal to 0. Right? So we want to set all of these to 0, and then we want to solve the corresponding system for that basis. Right? So this is the, I hope this notation is clear. Maybe I should, right? So in this case, for example, x bar b, if I'm looking at this as my x bar, is exactly going to be 4, 1, and 2. And x bar n is going to be the remaining entries, which are all 0, which is not a coincidence. The entries here do not have to be 0. I mean, they do not have to be non-zero. They happen to be non-zero in this example, and I think in all of the solutions we found. What is important is that the non-basic entries, they have to be 0, right? And when you solve the system for just those columns which are in the basis, you may get zeros somewhere, but you may not, right? So the important part is that this is 0. Okay, I think I need to put transpose everywhere. All right. Yes, I think I should make a note here. Some entries in x bar b may also be equal to 0. Okay. So all of these solutions that we found using simplex, in particular, they were basic solutions to the system ax equal to b for the corresponding bases that we have written down. All right. Right. Observation. Every basis of the matrix A is associated with a unique basic solution of the system ax equals b, right? Why is that? Well, if b is a basis, right, then the unique solution corresponding to this basis is for the columns that are not, for the variables that are not in the basis, you basically want there to be a 0. And for the columns that are in the basis, you want it to evaluate exactly to the right hand side, right? But because the rank is exactly, it's a full rank matrix on the left hand side, AB, what this is simply AB inverse times B, right? And so if you put these variables along with these, you get your unique solution x bar. Right? It's basically linear algebra. Okay, are there any questions or concerns at this point? All right. And notice that here we are just talking about the system. We are not talking about the linear program, but of course, our interest in is solving linear programs in standard equality form. So that for that reason, we are going to refer to a basic solution as being feasible if it is non-negative. Sometimes you might solve the system and you might get some negative entries in it. Okay. So A basic solution is a basic feasible solution. This is a term that we'll be using a lot, abbreviated to BFS.
Oh.
I think someone's mic is on. If it is non-negative. Okay. So in particular, all the solutions found by Simplex are basic feasible solutions. Okay. We are always maintaining that our solution is non-negative. So not only are we finding basic solutions, they are always non-negative, which means that they are basic feasible solutions. Right? Not all basic solutions have to be feasible. If you look at the columns 1, 2, and 5, so let's say you take 1, 2, and 5. So what do you have? 4, 1, 2, 1, 0, 1, and 1, 0, 0. If you take the bases 1, 2, 5, so the matrix AB is 4, 1, 2, and I forgot. Let's see, I have it here. 1, 0, 1, and the fifth column is 1, 0, 0. And if you compute the corresponding solution, so I'm just computing x bar b because the n is going to all be zeros. So it's AB inverse times our right hand side. And if you compute that, you get, I'm not going to compute the inverse here. Right, you get 4, 2, and minus 1. Okay, remember B is our same vector as before, 17, 4, and 10. Okay, so that's what you would get. And notice that this is a basic solution because B is a basis. You can see that these columns are actually linearly independent. However, the solution is not non-negative. So this is a basic solution that is not a basic feasible solution. Okay, so these are not the ones we want, but I just want to make it clear that not every basic solution is feasible. The non-negativity constraint is important, right? All right. Are there any questions or concerns at this point? Okay. Furthermore, we will say that a basis is feasible if it is associated with a basic feasible solution. Right? So in particular, this b equal to 1 to 5 is not a feasible basis because the corresponding solution is not a basic feasible solution, not a feasible basis. However, all of the bases found by Simplex, they are actually feasible bases. In fact, the plural would be bases. Okay. If it is not feasible, otherwise we say it is infeasible. Okay. Good. All right. So I think those are the main points I wanted to mention. I want to do one more quick example. So this was a do-it-yourself problem from yesterday. I just want to illustrate one phenomenon which I wasn't able to illustrate using this example that I had chosen. So this was from yesterday's do-it-yourself. So you are supposed to maximize x1 plus x2 plus x3 subject to the following constraints. In fact, I will just write it down in matrix format. 2, 6, 1, 2, 0, 4, 1, 0, and 0, 1. Yeah. And maybe let me just write this down as 1, 1, 1, 0, 0. Right. So we have two constraints and 5 variables, and then of course we have the non-negativity constraints. Okay. Did anybody solve this? Did anybody try it out? No one? Anybody has an optimal solution? Okay, so anyways, you should try it out. I'll tell you what the basis and the corresponding solutions are so you can check. I just want to illustrate what I wanted to. So here are the bases. Clearly, the first basis is you start with 4, 5, right? Because it's already the identity submatrix over there. And the corresponding solution is simply the right-hand side, 0, 0, 0, 4, 12. And the value is 0, right? The next basis, if you did it correctly, should be 1, 5. And the corresponding solution is 2, 0, 0, 0, 0. And the value is 2. And then you get 2, 5. The corresponding solution is this one here. And the value is 4. And finally, you will get to this basis 2, 3. And the value is 5. So if you are planning to do it, you can check that you are actually getting these answers. Right? What I want to, so notice that all of these are going to be feasible bases because Simplex is always finding feasible bases, right? So all of these are going to be feasible bases. I want to focus on one of these, which is interesting, this one. Notice that here we have a basic feasible solution which also has 0 entries in one of the basic variables. Right? So those variables which are in the basis, we call them the basic variables, and the other variables, we are going to call them the non-basic variables at any step of Simplex. Right? So notice that x bar n is 0, right? Where n is instead of 1, 5, it is the columns 2, 3, and 4, and all of those entries are 0. However, X bar B also has 0 entries. What is X bar B? It is 1 and 5, so it's 2, 0. Right? And notice that if I give you this particular solution, it is actually a basic feasible solution for multiple bases. X bar B in this example 2, 0 is a BFS associated with multiple feasible bases. For example, it is associated with 1, 5. Can anybody give me another possibility? What would be another feasible basis which would give you the same solution?
Uh, 1,4.
1, 4? Yes, indeed, right? It is also associated with 1, 4 because what does it mean? It means that all the entries in 2, 3, and 5 are 0, right? And the columns 1 and 4, they are actually linearly independent. So if you solve that system, you would still get the same solution. Right? So it's also feasible. It's also associated with this basis and so on. Right? So you can pick any two columns. You have to pick the first column because the first entry is non-zero. And then you can pick any of the other 4 columns that would form a basis with the first column. Okay. The reason I am mentioning this is because in the simplex method, at every step your basis will change, right? That should be clear from the way we did the example yesterday. Every time some variable enters and some variable leaves. So your basis is going to change. However, your basic feasible solution might actually remain the same in the next step. It doesn't have to change at each step. So we will actually see an example later, or it might be on an assignment. I'm not sure yet. So the important point here is that at every step of simplex, the feasible basis will change. However, the associated BFS need not change. In fact, what I would like you to do as a try it yourself problem, also to help myself, is if you can find an example and run the simplex algorithm on it and show me a point where the feasible basis will change because it has to change, but the basic feasible solution remains the same. Okay, see if you can construct an example where the BFS remains same for 2 consecutive iterations of simplex. Actually, let me remove consecutive. I'm not too sure if that can be done. Right? So if you are able to construct such an example, please post it on Piazza. I'm also going to try because I don't know of an example off the top of my head, but I think I've seen in the past. Okay. So you want to run the simplex method, and at 2 steps, you want to get the same basic feasible solution for 2 different bases, because the basis always has to change. Okay. Good. So I don't think I have much more to say today. I mean, I could say, but then I will be starting a new thing. Maybe I'll just wrap it up a bit earlier today. So one thing we haven't proved that the simplex method actually terminates in a finite number of steps. Okay. So that's something we still need to do. Of course, there is another possibility. So in the example we did yesterday, we started from a simplex which was already in a nice form. Okay. So we had the identity matrix and we had the right hand side to be non-negative. Right. Let's go back to our example. So we already found a feasible solution by just inspection, right? 17, 4, and 10. You give that to the last 3 variables and the rest are 0. So just by looking at this, we were able to get a feasible solution, and then we solve this using the simplex method. In particular, we found an optimal solution, and that was certified by our last dictionary. If you look at the last dictionary, it was 21 minus x5 minus x6, right? There is another possibility, is that your LP is unbounded. So we will also see an example either in the lectures or in your assignment, where the final dictionary actually tells you that the linear program is unbounded. Okay. Of course, there is one more thing remaining. What if I give you a linear program which doesn't have these nice properties? In particular, you don't see the identity submatrix somewhere, or the right hand side is not non-negative, right? So then how do you proceed? Because you want a basic feasible solution. So this makes it easy to find a basic feasible solution and start simplex, right? So that is another thing we need to address. Interestingly, there is a nice trick that is being used there. So in order to find a feasible basis, what we will be doing, we will write a different linear program that will already have a feasible basis. We will solve that, and solving that will give us a feasible basis for the original linear program, if one exists. Otherwise, it will tell us that the original linear program is infeasible. So that's coming up in maybe another 2 or 3 lectures. Okay. But right now we are focusing on the case where we already have a feasible basis, and from there we run the simplex method. Okay. So yeah, I think I'll conclude today's lecture here, because I don't want to start with a new topic and leave it hanging. All right. So that's all for today. If there are any questions or concerns, please stay back. I'm here for another 10-15 minutes.
Can we show that the points that we get through simplex, like the points that we were getting initially, where we're evaluating the function, they are all extreme points?
That is a good point. Thank you. I actually want to mention a theorem. I thank you for reminding me. So this, we are not going to prove it. It's actually easy. It might be on your assignment. So they are actually extreme points. Basic feasible solutions are exactly extreme points. So theorem 2.21 in one of the texts we are following is the following. Let A be a matrix with linearly independent rows. And B be a vector of the right dimensions. Okay. So let's say P is your polytope X such that AX is equal to B and X is at least 0, or polyhedron. Let P be this polyhedron. Okay. And let's say we take any point in this polyhedron. So it turns out that this point is an extreme point of the polyhedron if and only if it is a basic feasible solution for the system AX equals B. Right? So just to be clear, A is M times N, and what should be B here? Can anyone tell me what B should be? What should the dimension be?
N times 1.
M times 1?
Yeah, M times 1.
Right, exactly. Okay, so that's just implicit. Okay, so the extreme points of the polyhedron for this standard equality form linear program are exactly what we defined as the basic feasible solutions for AX equal to B. Remember, feasible automatically implies that we want it to be non-negative, right? That's by definition.
So then this would immediately show that simplex will converge in finite number of steps, right? I mean, if we are going from extreme points, the maximum number of extreme points probably will be, if we have lines, then it will be, if we have n lines, NC2 lines for,
Right.
so
Right.
we
There
have a
is one
finite number
problem.
of,
There is one problem.
yes, which is,
Can you, yeah, can you
uh,
try to see? We need to prove something. So, yeah, go ahead.
no, sir, actually, I'm not finding any problem there. That's why.
So there is, so maybe we'll see an example. Again, I need to construct and make sure that it's fine. So basically, you can get into a cycle situation. If you do simplex arbitrarily, you can actually come to the same basis,
Okay.
and therefore the same extreme point again.
Okay, so going from point 1 to point 2 again, we can come back to point 1 and we'll keep on.
Exactly. Exactly. So that is the problem. Don't worry, there is a
Okay.
solution to that problem. So in yesterday's do-it-yourself problem, we mentioned to follow a rule. Whenever you have a tie between the two entering variables, let's say two different variables can enter, right? Or two different variables can leave. You choose the one with the lowest index. For example, if you look at this, the second example I gave you here, let's say you write down the dictionary for this example, right? So what will your Z be? X1 plus X2 plus X3. You agree? So
Yes,
all
sir.
three variables X1, X2, X3 can enter. So because you have a choice, you always choose the lowest index, right? Basically, you do some ordering, and as per that ordering, you always choose the lowest index. Even in the leaving variable, if you have a tie, you choose the lowest index.
Okay.
This is called Bland's rule. And if you follow Bland's rule, it turns out that you can prove that simplex terminates.
Okay, so
Right?
the lowest index. Okay, I will
Yeah.
just look this up.
Right. So this is called Bland's rule. Yeah. So
It
maybe
looks
I'll just,
counterintuitive that this small thing can actually help us, but
yeah. So simplex may not terminate in general. However, using Bland's rule, it will always terminate. We probably might prove this in the lectures. I really want to prove it. Let's see if we have enough time for it. And what is Bland's rule? Always choose the lowest index variable whenever there is a tie. For entering or leaving variables. Okay. So yeah, we might prove this. Okay.
Sir, one more thing. Can you just show the A matrix that you had written above there?
Yeah, sure.
I want to ask regarding that.
This example?
Yes, sir. So
Okay.
here we are having this identity matrix kind of thing here, which makes life much simpler for us right now.
Right.
But
Right.
if we have that inequality kind of, where we have an inequality in our constraints, and we add slack variable, this identity automatically pops up, right? I mean,
That's right.
then okay, so okay, those conditions are even easier to solve them because they
Yeah. So
automatically have.
right. Right. If all of them are inequalities, or let's say all of them are less than equal to, right? Then you will just put the slack variables and you will immediately get the identity matrix.
Yes,
That's right.
that's what I was
That's right.
thinking. Okay, sir.
In fact, even the second point I mentioned, let's say you have a standard equality form, but you don't have a you don't have a nice form, right? You don't have the identity matrix or the right-hand side being non-negative. Even in that case, as I said, that there is a trick, and that trick looks very much like introducing slack variables. They are going to be called auxiliary variables. So it is actually, it will remind you of slack variables once again, but it's slightly different from that. Okay. So we will see that later. So I just want to give you a heads up that
Okay.
yeah, we are going to introduce new variables and write a different LP, and that LP will be in this form. And then we will solve that LP, and its solution will tell us whether the original LP has a feasible basis or not. Okay. And the trick we are going to use is similar to introducing slack variables, but we are going to call them auxiliary variables because they are not really slack variables.
Okay.
Okay. So you can also try that on your own if you want.
Okay.
Yeah. All right. Okay. Any other questions or concerns? Okay. If not, I'm going to stop recording now.